Hello folks, so this is next video on the series of electric potential and capacitance. So till last lecture we were discussing the charging of RC circuit, right? So let's continue with that and let's understand more on what is capacitor, how does we charge and discharge a capacitor. Before dealing with that, we talked about two components in last class, right? One is a resistor, right, which is indicated by this sign, and one was a capacitor, right, which is indicated by two parallel lines. So the equations which we use for capacitor, we already know it is nothing but q equal to cv, right? Q equal to cv, and hence v will be what? Q by c, right? For resistors we use equations like v equal to ir, which is Ohm's law, right? So we know the expression for voltage for capacitor and resistor, right? What about current? For a capacitor, if I need to find current, we know that current is nothing but rate of flow of charge, so dq by dt. So again, if I place q equal to cv, so it becomes d by dt of cv, it becomes c dv by dt, right? So this is expression for current in a capacitor, right? So it is product of capacitance and rate of change of voltage around it, right? Okay, so we were talking about charging of RC circuit. So charging of RC circuit. So we took one RC circuit, we connected it with a DC source of potential, let's say E. Right, this is a capacitor of capacitance C. This is a resistor of resistance R. Right. Now we need to understand what is the way this voltage source is charging this capacitor, in what manner, right? And how much time it is taking to charge and things like that. So we finally derived at an equation. We came at an equation that charge on this capacitor as a function of time will be given by CE and 1 minus e to the power minus t by RC, right? This is expression for charge on this particular capacitor. The voltage on this particular capacitor in function of time will be what? It becomes E into 1 minus e to the power minus t by RC, right? This is the voltage. What about current? Current, I already discussed, current is nothing but C into dV by dt. So if I differentiate it and then I find current, what will be the expression of current? So it becomes C, and differentiation of this becomes E, and then this becomes by RC, and e to the power minus t by RC. So this is nothing but E by R into e to the power minus t by RC, the expression for current, right? So now we have expressions for current on in the capacitor. We have expression for voltage across the capacitor. We have expression for charge on the capacitor. All are with respect to the function of time, right? And here we define one more term called RC, which is represented by tau, which is product of R into C, resistance into capacitance, and this is the time constant of RC circuit, right? Time constant of RC circuit. And we said that this is the rate by which we decide how fast or slow a capacitor is charging, right? And we also discuss that it takes approximately 5 time constants to completely charge a capacitor, which means 5 times RC, right? So if you want to choose the value of resistors and capacitance, let's say you are designing an electronic circuit and you need circuit which has faster response, which can respond faster. So you will need circuit which has better time constant, right? So that you can have faster charging of the capacitor, and you can store some energy, you can store some potential and more things like that, right? Now let's see graphically how these things looks like graphically, right. So now let's see that how these things when plotted on graph looks like. So charge as a function of time is given by CE into 1 minus e to the power minus t by RC. RC is the time constant, right? So if I need to plot charge versus time, let's say I'm plotting charge versus time, right? So at time equal to 0, at time equal to 0, you see charge is nothing but it is 0, which means capacitor is discharged fully, right? So this is my first point of interest. Time equal to 0, qt is 0. Again, at very high time, right? At time equal to infinity, let's say. If I place e to the power minus infinity, it becomes 0. So at time equal to infinity, qt becomes c into e, which is the maximum possible value of charge on the capacitor, right? And this condition is called fully charged condition, right? Fully charged. So at time equal to infinity, the capacitor becomes fully charged, right? And what about at time equal to RC, which is the time constant tau? So if you see at time equal to RC, the capacitor will have something like 63.63 of CE. If you calculate, you'll get it 0.63 of CE, right? Which is 63% of full charge. Now, if I plot all this graphically, the charge versus time nature will look something like this, right? So charge versus time will look something like this, and this is kind of a, this will be like a straight line here because it is, we are showing infinity here. So it as the time reaches infinity, this charge will reach maximum value, which is CE, right? CE. And remember that at t equal to time constant, right? At t equal to RC, which is equal to tau, this capacitor will be at 63% of its charge, right? I don't know what we talked in the last video, but see properly that at time equal to one time constant, which is 1 RC or RC, it will be at 63% of its maximum possible charge, right? And approximately we say that it takes around 5 time constant for capacitor to fully charge, right? We are telling that at time equal to infinity, you know, infinity is not a real number, so generally we say that at 5 time constants the capacitor reaches something like 99 point some percent, and hence we can say approximately it is fully charged, right? So this is how charge versus time looks like for the capacitor, right. Now let's plot current versus time, how current versus time looks like. So this is the current flowing on this capacitor as a function of time, and how this current versus time looks like. So this is the expression for current. So at t equal to 0, if you see, the current is nothing but E by R, right? So it is nothing but E by R, which basically means there is no contribution of capacitor. Capacitor is acting like a short circuit, like it is allowing all the current to pass through it, right? So this is like this is acting like a short circuit, right? This is acting like a short circuit, and this is the maximum possible of current which is flowing through this circuit. So at time equal to t, the current is E by R. What about at time equal to infinity, which is very high times? Again, if you say e to the power minus infinity will be 0, so current becomes 0, right? Current becomes 0 at infinite time. So which basically means when time is infinity, the capacitor is fully charged, and after that it is not accepting current anymore, it is not accepting any charge anymore, and hence it behaves like a open circuit, right? Open circuit, or I can call it as insulator. So behavior of capacitor is like insulator, and this is short circuit, which means conductor, right? And again, at time equal to t equal to time constant, which is RC, you can find what is the value of current, right? You can find what is the value of current. I'm not very sure. It may come something like 0.37 into E by R maybe, but you can calculate, right? And if you plot everything graphically, the graph will look something like this, right? The current versus time graph will look. This is the max value of current, which is E by R. It goes on decreasing, and at time equal to infinity, it becomes 0, and hence I am indicating it closer to the x-axis, right? Now let's talk about discharging of capacitor, right? Discharging, we just talked about charging. So when a capacitor has charged, now it will discharge, right? So discharging cases, let's say this is a RC circuit, and now this circuit does not have a battery. There is no cell in this circuit. So this capacitor initially is charged up to, let's say, Q naught charge, and has potential E initial. So at time equal to 0, right? Now I'm talking about discharging, right? So we say at time equal to 0, charge on capacitor is Q naught, and voltage across capacitor is E. Let's say this is E. Now we will see how the nature of this discharging. So what will happen when I connect, let's say initially this circuit is open, right? And capacitor retains its voltage, charge, everything. Now I connect this circuit, the capacitor will discharge, and there will be a current flow, right? It will discharge with some current, right? So we need to find out what is the value of that current, and what is the nature of the current and voltage profiles across it, right? Now if you see, there is no cell in the capacitor, right? There is no cell in this capacitor. So there is no cell in this circuit, right? So if you see the potential, there are two potential in this circuit. At any time t, there is a voltage across capacitor, there is a voltage across resistor, right? There is a voltage across capacitor, there is a voltage across resistor, right? Now, since when cell was supplying, we told that E equal to VR plus VC, right? The cell voltage is equal to voltage across resistor plus voltage across capacitor, right? Now in this particular case there is no cell, right? So it becomes 0 equals the sum of potentials across resistance and capacitance, right? So VR is nothing but IR, and VC is nothing but Q by C, right? VR is nothing but IR, and VC is nothing but Q by C. So 0 is equal to I is dq by dt into R plus Q by C, right? So dq by dt into R equal to minus Q by C, dq by dt equal to minus Q by RC, dq by Q equal to minus dt by RC. Now if I integrate this, right, if I integrate these quantities, so at time equal to 0, my capacitor charge is Q naught, and let's say at time equal to t, the charge on capacitor is Q, right? These are the limits of my integration. So integration of dq by q is ln q from Q naught to Q. It becomes minus T by RC. So if you integrate it, it becomes ln Q by Q naught equal to minus T by RC, right? And if you take anti-log across both sides, right, you will get that Q is equal to Q naught into e to the power minus T by RC, right? This is the expression for charge on the capacitor while it is discharging. So Q is nothing but equal to Q naught into e to the power minus T by RC. RC is again time constant. And similarly, if you calculate voltage across capacitor will be V naught, which is E initial voltage into e to the power minus T by RC, right? This is a voltage across capacitor. If I talk about current will look something like this: C into dV by dt. As always, current will look like this. So if I calculate from here, this will become CE into minus RC into e to the power minus T by RC. This becomes minus of E by R, e to the power minus T by RC. The current is negative because it is now discharging and flowing in the opposite direction, right? Now if I plot all these graphically, so one more thing, RC is again here the time constant, which is again the rate by which it is discharging, right? So RC is the time constant. Now let's plot all of this graphically. So let's plot these two things: charge versus time, right? And then current versus time, right? Current versus time. So you see that charge is q equal to q naught into e to the 1 minus t by rc. So at time equal to 0, q will be equal to q naught. So which is the maximum charge it is holding? So initial charge, right? Which, so when this charge has not started and it is at its maximum charge, and with time you see the capacitor charge will decrease, 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 and at time equal to infinity it will totally discharge, right? There won't be any charge. So nature of charge versus time will look something like this, right? Decrease, exponentially decreasing function. And even voltage versus time will look like something like this, right? Okay, this is voltage. What about current? What about current? So again, at time equal to 0, at time equal to 0, what is the value of current? So at time equal to 0, the value of current is minus e by r, which is again the max possible value of current, right? Again again when time will increase, the magnitude of current will keep on decreasing, keep on decreasing, and at time equal to infinity the current magnitude will reach to 0. So if I need to plot current here, this will be negative y-axis since it is a negative quantity, right? So at time equal to 0, the current is minus e by r, and it will somehow decrease, 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 and at time equal to infinity it will reach to 0. So current versus time will look like this. It is in the fourth quadrant, right? So this is how charging and discharging looks like. And at time equal to tau, which is at t equal to rc, if you calculate, this charge will be 37% of q naught, right? 37, even the voltage will be 37% of e, right? So this is the opposite case. In case of charging rc circuit, it was 63% at time equal to time constant. Here it is 37% of initial, right? Now let's solve some more problems on the capacitance, right? Now let's solve a problem on the general capacitor topic. So the problem says that these are the connection. This is a circuit which is given. It has a battery. It has 3 capacitors. So we need to find the capacitance between A and B. These two are A and B points. And then we need to find the charges on these 3 capacitors one by one. Right. So let's start with first part. Then we'll go to the second part. Right. So to find the capacitance between A and B, I need to turn this circuit to something like this. This is C equivalent, this is A, this is B, and this is connected to a battery of 24 volts, right? So this is C equivalent is what we need to find. What is C equivalent, right? So you know the 12 microfarad and 6 microfarad capacitors on the top, they are in series, right? You can easily say they are end-to-end connected. So this is an end-to-end connection. So these capacitors are in series, right? So if I try to make these capacitors as one and then parallelly connect a 2 microfarad, can I do it? Let's say this is C1. Can I make it like this? And what will be the value of C1? So C1 is the net equivalent capacitance because of this series combination of 12 and 6, right? So I can say that 1 by C1 equal to 1 by 12 plus 1 by 6, which becomes 12, 1 plus 2. So C1 becomes nothing but 4 microfarad, right? C1 becomes 4 microfarad. So series combination of 12 and 6 is 4. So my final circuit is 4 microfarad here, right? So now I have a parallel combination of 4 and microfarad capacitor and a 2 microfarad capacitor. So net equivalent capacitance will become 4 plus 2. Very simple. This becomes 6 microfarad, and this value we found as 6 microfarad, right? This is very simple. We just need to analyze what all branches are in series and parallel, right? So this becomes 6 microfarad. So first part is capacitance between A and B is 6 microfarad. This is solved. Now we need to find the charge on the 3 capacitor, right? Charge on the 3 capacitors, right? So if you see, battery will supply one charge, right? Let's say battery is supplying Q. This Q will distribute as 2 charge over here at point A. Let's say this becomes Q1 in this branch and Q2 in this branch. In series, charge is always same. So this 12 and 6 will get the same charge, but this 2 will get a different charge. We need to find what is Q1 and Q2, right? What is Q1 and Q2? Okay. First, let's find this net charge which is supplied by the battery, right? So charge is nothing but C into V. Q is Q equal to C into V, right? So net capacitance is 6. Net capacitance is 6, and net voltage is 24, right? So what is my net charge? This is also Q, so this becomes 144 microcoulomb, right? 144 microcoulomb, right? Now this 144 microcoulomb charge, 144 microcoulomb charge is entering as Q1 and Q2 in two separate branches, which is this is 12 microfarad, 6 microfarad, and this is 2 microfarad, right? So this is entering as two types of charges here. But overall, if you see the energy conservation of charge, it says that Q1 plus Q2 will be 144. So either I can find one of them and then I'll be able to find the net charge. So since I have only one branch here, let's find for the Q2. So Q2 will be what? Q2 will be nothing but C into V again. But here C will be 2 microfarad. But voltage is again same, which is 24. So 2 into 24, which is 48. And from 1, if you see, Q1 becomes 144 minus 48, which becomes 96. So this is Q1. So this capacitor gets 96, this gets 96, and this will get 48, right? So we found what are charges on these three capacitor, right? Let's solve the next one. So let's solve one more problem on this topic. So this is a capacitor which is given, right? The question is we need to find the capacitance of the system. So without dielectric, the capacitance of the system was C, right? This is the capacitance of the system when there was no dielectric. Now is the question is, three different dielectrics are placed in this manner. They are having dielectric constant as K1, K2 and K3, right? So we need to find what is the change in capacitance and what is the new capacitance after we have inserted these three dielectrics over there, right? If I write initially, right, let's say area of plates is A. Let's say the area is A. Distance between plates is D. We are assuming all that. So initially C will be nothing but epsilon A by D, right? Formula for a parallel gate capacitor is K epsilon naught A by D. But initially when there was no dielectric and there was air, K becomes 1. So it was epsilon A by D. So C is nothing but epsilon A by D, right? Now, when we have three different dielectrics over here segregated in equal areas, so area which this dielectric takes K1 is A by 3, K2 also takes A by 3, K3 also takes A by 3, right? But the distance is again same for all of this, which is D. But if you see, if there is a charge coming off here, right, if there is a charge coming up from this terminal, it gets segregated between these three systems, right? So something like a parallel combination, if you see, they are having a common potential. VAB is the common potential, be it whatever is the dielectric, but any charge which comes gets segregated in these three regions, right? So this is like a parallel combination of three different capacitors, right? This is like a parallel combination of three different capacitors. Let's find individually capacitance of all three, and then we will find what is the net capacitance, right? So capacitance of this, let's say the first one, for the first capacitance is C1, for this one capacitance is C2, and here it is C3. So C1 will be nothing but K1 epsilon naught A by 3 upon D, since it is in the 1/3 of the area. So this becomes K1 epsilon naught A by 3D. Similarly, if you see, C2 becomes K2 epsilon naught A by 3D. C3 becomes K3 epsilon naught A by 3D. And since this is a parallel of C1, C2, C3, this is the system is like this. So net capacitance will be C1 plus C2 plus C3. And if I take all common, this becomes C epsilon naught A by 3D into K1 plus K2 plus K3. And epsilon naught A by D is nothing but C. So this becomes C by 3 into K1 plus K2 plus K3. This is net capacitance now. So after putting or inserting dielectric, the net becomes capacitance becomes C by 3 into K1 plus K2 plus K3. Right. Right. So next problem is find capacitance of this infinite ladder. Right. So this is an infinite ladder. You see this ladder is extending till infinity, right? And you see a series and parallel combination of capacitors over there. Some connected in a straight manner, some connected in a vertical manner, and this is going till infinite, right? So you'll come across these type of problems even in your next chapter on the current electricity, where we will deal with resistors. So how to approach this type of problem, right? So if you see, since this is infinite circuit, right, this is an infinite circuit, but we need to find from which point the repetition starts, right? Like which pattern is repeating infinitely, right? We need to find that pattern first, right? So if you see, if I make a marker over here, you see that this particular pattern is repeating again and again. This pattern is repeating again and again and again in the same manner, right? So this is, I have identified the pattern which is repeating infinitely. And if let's say this point is P and Q, right? So infinity is a very big number, right? It is a very big number. And if I take 1 or 2 from infinity, they generally don't make any difference, right? They don't make any difference at all, right? So if I say that, let's say capacitance between A and B, right, is equal to C1. So we need to find capacitance between A and B for this particular problem, right? And we assume this capacitance as C1, right? But if I skip this, right, if I skip just one of this pattern which is repeating infinitely, and if I find capacitance between P and Q, so if I skip this only, I'll start with P and Q, and if I find capacitance between P and Q, that should still be C1. Capacitance between P and Q should still be C1, because if I take in 1 out of infinity, it won't make any difference, right? So if I draw it diagrammatically, so this circuit can become something like, this is C, this is again C, and this becomes C1, right? This becomes C1. Resultant is C1, and this is also as equivalent to this resultant, right? Now let's solve this problem using analytically series and parallel methods, right? So this C1 and C, this C1 and C are in series, right? This C1 and C are in series. So if you solve by series formulas and all that, you can easily say that the net of this C and C1 will be nothing but C into C1 by C plus C1, and this is A and B, right? Right, this is A and B. Now capacitance between A and B, now it is the parallel combination of this. So capacitance between A and B is C plus CC1 by C plus C1, and this is what is again C1. So C1 equal to C plus CC1 by C plus C1, right? C1 equal to C plus CC1 by C plus C1. Now we need to find what is the value of C1 by solving this equation, right? Let's make an equation over here, right? This becomes CC1 plus C1 square is equal to C square plus CC1 plus CC1, right? So this becomes C1 square equal to C square plus CC1. So C1 square minus CC1 plus C square equal to 0. This becomes a quadratic equation now, right? This becomes a quadratic equation now. Now this becomes a quadratic equation here, right? So yeah, this would be minus of C square, right? This is my equation. Now you can easily find C1 using quadratic formula, right? So what is quadratic formula? You already know. See, it is minus b plus minus under root b square minus ac by 2a. So if I use that and put it here, so this becomes under root c square plus 4c square by 2, right? This becomes like that. So this becomes C plus minus under root 5 C by 2. I can ignore the negative value, capacitance cannot be negative. Let's ignore this negative thing. So this becomes C plus root 5 C by 2. So C into 1 plus root 5 by 2. So this is my equivalent capacitance, right? So all these infinite ladder problems, right, should be solved in a similar approach, right? Where you should first find what pattern is repeating. You should identify one pattern, and then you should know that infinity is a big number. Even if I remove one pattern out of that, my net capacitance, net effect and things won't change, right? Let's go to the another one. Let's solve the next problem. So the problem states that if 100-volt potential is applied between A and B, we need to find the potential difference between C and D, right? So let's say this A and B, as of now, this is open circuit. There is no cell source. Now what we are doing is we are connecting a cell or battery of potential 100-volt here, right? So this is my new diagram. Now, after that, I need to find potential difference between C and D, which is potential difference across this specific capacitor, 6 microfarad, right? This 6 microfarad, right? You know, for capacitors, Q equal to C into V, right? You need to find the potential. So potential is nothing but Q by C, right? Charge by capacitance. But you don't know what is charge on this capacitor, right? You don't know what is the charge. Okay, let's find out what is charge flowing through this capacitor, and then we can easily calculate, right, what is the voltage across this. Like, let's say this capacitor, this battery is supplying net charge as Q, right? The battery is supplying net charge as Q, and this is getting distributed as Q1 and Q2 over here, right? So first let's find what is Q, then we can find what is Q1, and then we can find what is potential across this, right? So if I draw this diagram, you see this is 100 volt, right? If I redraw this, and this is a 6 microfarad capacitor, and if you see these two 6 microfarad capacitors are in series with each other, right? These two 6 microfarad capacitors are in series with each other. So equivalent will be what? 1 by 6 plus 1 by 6. So C equivalent will be 3. So I'll replace these two series capacitors by 3 microfarad capacitor, right? If I again break this, right, I am finding this, I need to find this Q first, right? So Q is still there, same charge is going. If I again break this, this becomes parallel combination, which becomes 9 microfarad, which is connected across 100-volt battery, and charge is Q, right? So now I can find what is the net charge supplied by battery, which is C into V. So 100 into 9, right? 100 into 9, which is